Okay, so in this video, we are going to consider what infinite geometric series could look like, and if there are any rules we could use specifically for these cases and what those rules might be. So clearly, sometimes we can actually add up all of the terms in a geometric series to an actual finite number, even though it's infinite and goes on forever. Let me give you an example, okay? And I'll use a geometric example. So think about that square. I know it's not a very nicely drawn square, but it has an area of 1. And if I added to it another little rectangle that had an area of a half, and then another little square that had an area of a quarter, and then something else that had an eighth and a 16th, and so on and so on and so on, right? A 1 over 32, a 1 over 64. You can see the idea, right? Okay. What I'm getting at here is that the sequence 1 plus a half plus a quarter plus an eighth plus a 16th. You get the idea. Now, clearly, this is geometric, isn't it? Right? Can you think what the U1 and R is going to be? This is going to go on forever and ever and ever. But I can tell you now that if we added it all up, can you see it's going to equal 2, right? And not just almost 2. It's going to exactly equal to 2. 1.9 reoccurring is 2, right? So we can say it has a finite sum. However, some sequences that are geometric, for example, the most obvious being 2, 4, 8, 16, well, that is going to get infinitely big, and that is not going to add up to a finite number. So some are going to do that, and some are not going to do that. So how do we determine which is which? Well, the difference between these two sequences is the value of r. R, in the first case, is less than 1, and that is what we need. We need to have a situation where the magnitude of r, and that's what those lines mean, okay, the magnitude, I don't care if it's negative or positive, has to be less than 1. Now, if that is the case, then we say that the series converges. And that is the name, right? Okay, converges. Now, let's think about it now in terms of our formula, right? So let's have a little think about this. And this time we're going to start with this formula, but we're saying for sure that r, the magnitude of r, is less than 1. All right, so if that is the case, well, let's think about this thing here, r to the power of n, right? R to the power of n, as n gets really, really big, so the 100th term or the 1000th term of the sequence or the millionth term of the sequence, well, a fraction, so something less than 1, with a large exponent, that is going to tend towards 0, isn't it? It's going to get smaller and smaller and smaller. So that's going to happen as n tends towards infinity. So going to our formula, we can say if we have this magnitude of r being less than 1, well, our formula for s of n, and we're going to go for s infinity now, we'll change the notation because we're looking to sum all of the terms that there are, not just stopping at some arbitrary number n. Well, that is going to be u1 bracket 1 minus 0. There's nothing there because that's going to tend towards 0, which is actually going to give us the overall formula of the sum to infinity is u1 over 1 minus r. And this is our important learning point for this video. That is the formula for a sum to infinity, but it only works if that magnitude of r is less than 1. So let's see it in action. Let's do a couple of quick, easy examples so you can work, so you can do your question set. So here is a infinite geometric series. We have u1 is equal to 18. So we can easily find r by doing one term divided by the previous. So can we see that's going to be 2/3 in this simple case. So our formula, if we're going to add all those up forever and ever and ever, our sum to infinity is going to be 18 over 1 minus 2/3, right? The sum is going to be u1 over 1 minus r. Well, that is going to be 18 divided by 1/3, which is 18 multiplied by 3. And if we work out 18 multiplied by 3, we're going to have, well, 18 times 2 is 36, 44, 54, right? We're going to have that summing to 54. Let's try another one. This one looks a bit more complicated, so we'll have a quick go at this one. So we've got to sum these terms. So again, u1 is equal to 8. R looks a little trickier to find, so let's just work it out. We're going to have, let's just say 4 root 2 divided by 8 is our R. Well, that is going to be root 2 over 2 if we just cancel the 4 with the 8. Look, okay, so we've got our values. Let's just pop them in. So again, S infinity is U1 over 1 minus R. So for this example, we are going to have 8 divided by 1 minus root 2 over 2. Now, we should probably simplify that. Let's write that down instead as 2 over 2 for our 1. So 2 minus root 2 over 2 would be a better way of writing that. So that is 8 multiplied by 2 over 2 minus root 2. So a way of writing that would be 16 over 2 minus root 2. Now, we are kind of finished there. However, I can't leave it like that because we've got a irrational on the denominator. So we'll just rationalize the denominator, which hopefully you've seen before. If you want to leave that as your final answer, I'm okay with that. But we're going to times that by 2 plus root 2 over 2 plus root 2, the conjugate of it. So that is going to give us 32 plus 16 root 2 on the top, and then on the bottom we're going to have a 4 and a minus 2, so we're going to have a 2. This will simplify to be 16 plus 8 root 2, and there is our final answer. Okay, so hopefully you've understood a little bit there about infinite geometric series and you can answer your